So the question was about the fall 2016 final exam, question 4D. Okay, a set instance represents a set of integers as a binary search tree. We did cut this concept of a binary search tree from the course, so I guess this particular question wouldn't be asked again, but I can tell you what that is, and you probably know. A binary search tree is a tree where every node has at most two branches.
Mm-hmm.
There's a left branch and a right branch. They could be empty.
Okay.
But the labels in the left branch all have to be smaller than the label at any particular node.
Okay.
And the labels in the right branch have to be bigger.
Okay.
So, and this is true for every subtree within the binary search tree. So anywhere you look, you have a root, which is the root of that particular subtree.
Mm-hmm.
And that root has to be larger than everything is left and smaller than everything is right.
That's
Now, here's the messy bit.
Mm-hmm.
In our tree representation, the one we've covered in this class, there's really no sense of like left and right branches
Mm-hmm.
if there's only one branch.
Mm-hmm.
Is it the left one or is it the right one? And this distinction is important for binary search trees because you can have an empty left branch, meaning there's nothing smaller than this root label,
Mm-hmm.
but a full right branch, meaning there's a bunch of values that are larger than the root label. And
Okay.
so you need a different class to represent these things
Mm-hmm.
than a tree class like the one we have.
Yes.
Because you need to be able to say that there's one branch and it is the right branch, or there's one branch and it is the left branch. Ours doesn't really have the capacity to do that. It just gives you that there's one branch. So in earlier versions of this course, we had two different classes. We had a tree class and a binary tree class, and they were quite different actually, which is why this was removed. It's because they sound really similar, but they had these quirks that everybody confused. So what were they? Well, tree class is the same as the one you know.
Mm-hmm.
The binary tree class always, every instance had exactly two branches, except that some of those branches were empty, meaning that they weren't really there.
Okay.
So if there was just a left branch, you would really have a left branch and a right branch represented as instances, but the right branch would be empty and the left branch would be full, and vice versa if there was only a right branch. So this was just a way of keeping track of which the one branch was if there was only one of them. Okay, with that long explanation, let's take a look at this question and see what we're looking at. A set instance represents a set of integers as a binary search tree. The node values are stored in a flat list called items. Implement the find method, which returns whether an element is in the set, and if not, adds it as a new leaf if the argument add is true. A set of ins stored in a binary search tree described by a flat list. So we're going to add k for all this stuff. And is there like relevant stuff earlier parts of this question or not really?
Yes.
Oh, I see. A flat list is a thing. A flat list is a list containing integers and none that describes a binary tree of integers. The root element is 0. The left branch of element I is 2 times I plus 1. Right is 2 times I plus 2. Okay, so every list describes the tree. All right, that was a very fast explanation. You know, if you're watching this at home and you want to follow this question along, you should probably read this more carefully, but I think I got it because I wrote it once upon a time. Okay, so we want to basically populate one of these lists that represents a binary tree, where this represents the root, this is the root of the left branch, this is the root of the right branch, this is the left branch of the left branch, this is the right branch of the left branch, etc.
Mm-hmm.
Okay, this example just shows that it works. Oh, 1, 3, 4, 6, 8, and 9 are all in there. And if you add 3 and you add 2, then it knows 3 is in there and 2 is not, but now 2 is in there. And there it is at the end. And why is it there? Well, it's the right branch of the left branch of the left branch of the root. Okay, so you said you had too many nuns. Like maybe you have exactly these values with a bunch of nuns at the
Yes.
end.
Yes.
I mean, that's kind of not wrong. In fact, I remember scoring this question, and we didn't detract from that because uh, having a bunch of nuns at the end just means that um, there's nothing else in the tree, but you've written a list that's longer than it needs to be. So maybe we can figure out how to do it without so many nuns.
Okay.
And let's keep reading. Okay, so add calls find with true, has calls find with false, and now we have to do the find where we track the index. I guess an easy thing to do is say, well, I is less than the length of self.items.
Mm-hmm.
If item self.items I is equal to V, then we return true.
Yes.
Otherwise, we update I. And we need to use this. The left branch is 2 times I plus 1, and the right branch is 2 times I plus 2. So in general, what branch we're going to depends on whether we're going to the left or the right. So if self, oh, I guess I should start writing instead of just shouting. Well, I is less than self.items. We take 2 times I plus 1 plus V is greater than, I guess we should write int, V is greater than, something like that.
Mm-hmm. Mm-hmm.
Okay, if we run this long enough, now I describes where V would have been in the tree if it had been there. Yeah, this while loop is responsible for iterating through the tree. I guess we need another term here, though, don't we?
Mm-hmm.
We need like a self.items I is not none. Yeah, so this basically searches through the tree. You know, if you went off the end, then it's basically like this 6, 3, 8, 1, 4, none, 9, none, 2 also has just a bunch of nuns at the end, which
Mm-hmm.
means there's no more tree there.
Mm-hmm.
But sometimes those didn't exist. So you need this check to make sure you don't go off the end, and you need this check to make sure you haven't reached a point in the
Mm-hmm.
tree where there's no more tree. If you've if self.items I is none, or you've gone off the end, then the V that you're looking for is not in the binary tree so far. So what do? You make sure, well, you set self.items I to be that value. But you want to make sure self.items I actually exists. So you could
Mm-hmm.
put a bunch of nuns at the end until you have room. And here's where you might add too many nuns. It's not really that bad to do it. But if you wanted to add the minimum number of nuns in order to make sure that self.items I existed, then I think you would
Mm-hmm.
add this many nuns. The I plus 1 that you're looking for. So you need a length of I plus 1 in order to set self.items I minus the length of self.items as it is now. Well, this is just like,
So
this is the like shortest number of nuns that you could add for this to work. If you added even more nuns, you know, you added another 12 at the end, you haven't really done anything wrong.
uh-huh.
But you've added a bunch of nuns that don't need to be there. So basically,
So
like any integer here that's this number or larger is fine. It would be correct. But this is the smallest one that you could do without having this line crash. So I came up with this because I just looked at what we're going to do. We're going to assign to self.items I, which means self.items needs to have length I plus 1. Otherwise, this will crash. And how do I get it to length I plus 1? Well, I need to add some stuff to the end. And this much is already there.
mm-hmm.
If there's 12 already there, and I'm trying to assign to number 15, then I needed to have a length of 16. So I've
I
got
see.
12 already. I need another 4. How do I get that 4? Well, 16 minus 12. So
Okay.
that's like, basically this just says extend the list until this is going to work. But if you made it even longer, that's not wrong. It's just
Uh-huh.
maybe a little bit inefficient. Sure. And just to reiterate for those watching from home, uh, if you don't know what a binary search tree is, that's okay because we didn't cover it. Um, but most of the rest of this problem, I think, is in scope in the sense that it's a fact that you could represent a tree where everything has at most two branches as a list, and here's a way to do it. And you weren't supposed to know that beforehand. This is something that was basically explained on the exam, and then you were supposed to work out its implications. But binary search trees are not in scope for the final. All you have to know is about trees. And yeah, is a binary tree in scope? A binary tree is really just a tree
It's at most
that's
two
not
branches.
allowed to have more than two branches, and none of its branches can have more than two branches. So that's in scope because I could explain it in like 8
Okay.
words.
Okay.
Um, it's not something you're supposed to know in advance, but it's certainly something that could be on the exam just because I could say like, oh, imagine that you have a tree that where no subtree has more than two branches. I think that's something that might happen.
And
Yeah, so I don't think I would. I mean, obviously, I won't ask this question because I already asked it before. But it was more appropriate in previous semesters when we spent a while talking about binary trees and binary search trees. There used to be a whole lecture on that, and that lecture is gone for two
okay.
reasons. It was like a lot to have these two different tree classes and keep them straight, and also you cover this again in 61B, so I didn't really need to cover it in 61A anymore. Yeah, there's actually a lot of problems like this in 61B where it's um, it's more about getting tree structures to allow for efficient computation. So most of 61A you have trees because you have tree structured data, like a tree structured scheme expression or something like that. And in 61B you see a lot of trees, but the point of the trees there is just to make other stuff fast, like representing a set or a dictionary or something like that. Someone asked about the following question from the fall 2019 final exam, which I will read and then we will attempt to solve. Implement tops, a generator function that takes a tree instance T. It yields all leaf labels in T for which the path from the root to that leaf is strictly increasing. The sequence is strictly increasing if each element is larger than the previous element. So 2, 3, 4, 5, but not 2, 3, 3, 3, 4, and not 2, 4, 3, 5. A path from a root to a leaf is a sequence of labels that includes the root label at the start and the leaf label at the end. So you just like walk along the tree, looking at each value along the way, and that has to be a strictly increasing sequence, something that is going up. Tree class is on the study guide. Okay. And it says you may not modify the attributes of any tree or write else and or square brackets. So I guess when you see that, the key is that you shouldn't be assigning to any tree's label. You can look up the labels, but you shouldn't really be changing any attributes. So I wouldn't expect to see t dot branches equals or t dot label equals anywhere in the solution. So if I have a tree with only one element, that node is a leaf, a path from the root to that leaf just has one element in it, and that is this label 1. So now we have a sequence of length 1. Is that strictly increasing? Well, apparently it is, because this got included. I guess, is each element larger than the previous element? This really should have been specified in the question, but since there's only one element, then we call it a strictly increasing sequence. Okay, so good thing we had this example to clarify that. I think this already gives us an indication of what to do when we reach a leaf, which is that we want to yield this label. Now, an interesting question is, are we supposed to yield t.label, or are we supposed to yield a list containing t.label? The answer is that you yield t.label. It's actually part of the doc test that creates a list. It's the job of a generator function to say what are the elements in that list, and it yields each of them. So when you're down to just one leaf, there's only one thing that you're responsible for yielding, and that's the current label. Now, we're only supposed to yield some of the leaf labels. We're supposed to yield the ones that are at the end of an increasing sequence. But this template doesn't really let us check what's above us in the tree. And that's not that surprising. A lot of times when you're doing tree processing, you don't really know where in the tree you are when the recursive call is made. We're making this recursive call on some branch, some subtree within the original tree. But by the time we get here, we don't really know where we are. We know it's a leaf, but we don't know that it's a leaf that was part of some larger structure, or if it was a leaf that's the whole thing. So at this point, the only thing we can do is just yield the label. But that means the filtering that gets rid of any paths that are not strictly increasing has to happen before we make a recursive call. Okay, so now we know we're not at a leaf, which means we're not going to be yielding t.label because it's not a leaf label. But we might need to yield leaves that are below us somewhere. So we'll go through every branch. I think here is a good opportunity to check that the path that we're on is strictly increasing. So how would we do that? Well, the only things we really have to work with are t.label and b.label. And what are these things? Well, I think we need an example tree, and here's a perfectly good one. So there's another path that goes from 1 to 3 to 4. That one's strictly increasing. But then there's one that's 1 to 3 to 1, and that's not. So back to solving the problem. If I call tops on the whole example, this thing is called EX, then I can see that this path looks like it's increasing for now. This path looks like it's increasing for now. And this path looks like it's increasing from now. Because in all cases, the label of the branch is bigger than the label of the root. So then I'd make a recursive call on each branch. Here, we'd reach a leaf, and so we would yield its label. Here, we would not reach a leaf. Now, in the recursive call, t would be bound to this tree. And in this tree, the label of the branch is smaller than the label of the root, which means that we are on a path that is not strictly increasing. So that's the information we needed in order to try to. So I think what I want to say is if it's the case that t's label is less than b's label, then if I get all of the labels at the end of increasing paths here, they will also be labels of increasing paths here. Yield from the result of calling tops on B. Yield from, it's really kind of a convenience. Instead of having this line of code, I could have had the following 2 lines of code. And this is true for every yield from, is that it's equivalent to saying for every x in tops B, yield that x. So yield from says yield every element in an iterator. In this case, a generator that tells me all of the labels within the branch that are at the end of strictly increasing paths. So if you find all the labels in the branch, then you've also found labels in the whole tree. Why would we make a recursive call in each branch? Let's say this was a simpler problem that was just yield all leaf labels. Then one way to do that, the simplest way I think, is to say if t is a leaf, you yield the leaf's label. Otherwise, you go through all the branches and yield all of the leaves in each branch. So that'll get you all the leaves. If you want the leaves for the whole tree, then go through all the branches and get the leaves for each branch. And so I'm going to erase this for now. If our goal was just to yield all of the leave labels, then we'd just get rid of this line, and we'd have a generator function that said, if T is a leaf, yield its label. Otherwise, go through all the branches and yield from the leaves in that branch. The only thing that's different about this case is that we don't want all the leaves. We just want the labels from the leaves that are at the end of these paths. So we need a way, as we're going and recursing through the tree to find all the leaf labels, to detect whether we're on an increasing path or not. So we put this if in here to basically say, I want it to still be increasing, then I keep looking for leaves. But as soon as I find a case where I transition from a root to a branch label and it goes down instead of up, or it stays the same, then I stop looking because I don't want any of the leaves from there. I want to go off and find another branch. So the question was about fall 2018's final exam questions 3, B, and C, but I think we got to kind of read through the whole thing in order to get there. So let's take a look. Sequence is near increasing if each element beyond the second is larger than all the elements preceding its previous element. So element I must be larger than element I minus 2 and L minus 3 and I minus 4, but it doesn't necessarily need to be bigger than I minus 1. So an increasing sequence goes 1, 2, 3, 4, 5, 6, but a near increasing sequence could go 1, 2, 3, 5, 4, 6. And the 4 is okay because the only thing bigger than it is the previous element. I think that's kind of the story. Okay. Whenever I read a definition, I try to figure out an example. Implement, but if you can't do that, then you could probably just look in the examples that are provided. So implement is near, which takes a sequence S and returns whether its elements form a near increasing sequence. Okay, so we're going to be able to iterate through this thing and figure out whether it's the case that it's near increasing. I mean, I guess we just like write down the definition for this one. There's probably lots of ways to do this, but let's just write down the definition, which would be that you go through for range 2 on, and you want to make sure that SI is bigger than everything in S from 0 to I minus 1. I think that's basically just a translation of the definition. Implement fast near, which takes an iterable value and returns whether its elements form a near increasing sequence. It must run in theta n time and theta 1 space. Recall that in this semester, we will not have efficiency on the final, so this would be out of scope, but I think we can go through it anyway. Like, how do you get fast near to run quickly? Well, what was not quick about this is like, I had to go through every I, and then I had to take a max over I different elements, and that would lead to what's called quadratic time. So this is kind of a slow way to do it because you have a really long list, and you have to go through and take the max of sublists over and over and over again. Okay, so we got to find
max is a linear function.
Yeah, max is linear.
Okay.
Okay, so implement fast near, which takes an iterable value and returns whether its elements form a near increasing sequence. Fast near must run. Okay, I read that part. Assume S has a finite number of elements. Okay, that's good. And we can't call is near. Then there's a funny thing in the template, which says you take in the list S, you build an iterator out of it, and then you're not allowed to refer to the list itself because we've bound to S to none. So we can only refer to the iterator. So this problem is kind of forcing us to use the iterator instead of indexing into the list directly. And the only two things you can do with an iterator are, well, the only one thing you can do with an iterator really, well, there are two things. There's two things you can do. You can call next on it, and you can pass it around. So you could like pass it into a new function or give it a new name or something like that. But the only thing that you can do that like makes progress is to call next on T. Okay, so then here's something else that's not in scope of the semester, which is exception handling. But I'll just remind you, if you happen to watch the optional lecture, which is, you should watch it, it's a good one. This allows you to call next on T, even if it might be the case that T doesn't have a next element. And if T doesn't have a next element, then this line is going to be executed. So this try, except, stop iteration basically says, do whatever this says, but if you called next on T and there wasn't a next element, then return whatever's on this line. Okay, so let's actually think about what's going to happen here. I think we are going to keep track of the 2 and the 5, and then we're going to focus on the 3. And the 3 is okay as long as it's bigger than 2 or anything before it. The 3 doesn't really care about the 5. But then we're going to process 6. 6 doesn't care about the 3, but it does care about the 5, which is important because that means we needed to keep around the 5 long enough that when we move from, we've processed this element already, and now we're trying to process this element, we have to know that it's not only bigger than 2 or whatever's before it, but also bigger than 5. So we'll probably take the max of whatever was the largest before and the last element. Okay, so I think that's enough to get me started because I have kind of a plan. I need to keep track of the 2 and the 5, which would be 2 and 5. If there wasn't a next, that means this thing was empty or it had only one element. In either case, I think it seems reasonable to call that
True. Yeah.
near increasing or whatever it's called. Yeah, near increasing. Okay, but you know, that's just like a boring edge case. Now we're at the case where we have at least 3 elements, or at least 2 elements, and what do? Well, we go through each new element if it's the case that X is less than or equal to the largest thing I've seen so far, then it's not near increasing. Now, the largest thing I've seen so far needs to be updated to be the max of the largest thing I've seen so far, and the last thing, that's like the number 5, which we didn't include, but we need to include next time. And then we need to keep track of whatever X was, because eventually that needs to be put in the largest, but not just yet. So now we can do a little tracing. Largest and last are bound to 2 and 5. X is bound to 3. 3 is checked against 2. And since 3 is bigger than 2, we get to keep going. At which point we bind largest to the max of 2 and 5, which is 5, that's good. And last to the number 3. And then X is bound to 6. 6 is compared to largest, which is 5, and it's okay, so then we keep going. And we rebind largest to the max of 5 and 3, which is 5. So that still represents the largest thing we've seen so far is 5. And last is bound to 6.
Mm-hmm. Yep, I'm following.
Okay, I guess that's kind of the end of the story. Now we go on to part C. Here's an alternative definition that's equivalent to the one on the previous stage, but stated in a more useful way for the problem below. A sequence is near increasing if each element but the last 2 is smaller than all elements following its subsequent elements. That is, element I must be smaller than elements I plus 2, I plus 3, I plus 4, etc. Okay, so you can work backwards or forward, and if it's near increasing one way, then it's near increasing the other way. Interesting. Okay, so implement near, which takes a non-negative integer n and returns the largest near increasing sequence of digits within n as an integer Okay, so I guess the reason we need this alternative definition is that when you process an integer by digits, you tend to go from the last digit toward the first digit, because that's the way to do it. You just divide by 10 a bunch of times. Okay, so implement near, which takes a non-negative integer n and returns the largest near increasing sequence of digits within n. Smallest and d are part of the implementation. You must determine their purpose. You may not call is near or fast near. You may not use any values except integers and booleans in your solution. No lists, no strings, etc. Okay. So sounds like we're gonna do some tree recursion. Okay, so in one case, you don't use the last digit, which means you get rid of the last digit, and you don't change this thing called smallest and d. I think smallest probably needs to be there to check and make sure that we can include n divided by 10 without violating the condition, which says that the smallest digit we've seen so far when processing from the end backwards has to be larger than n%n, which is the last digit of n. Then we're allowed to include the last digit in n. So what would that look like? That would be, we find the biggest non or near increasing integer in n divided by 10, and then we put n%10 at the end. If you want to build up all the different numbers contained within an integer, you look at the whole integer and you say, the last digit is going to be in there or it's not. So I could ignore the last digit, which is what the no case does, or I could keep the last digit, which is what the yes case does. But what does it mean to keep the last digit? Well, that means it stays as the last digit of the result. What about all the other digits of the result? They come from n divided by 10. Now, if you have a bunch of digits here, like 1, 4, 3, 5, 7, and this is 6, how do you put them together into 1, 4, 3, 5, 7, 6? You multiply this one by 10, so you got a 0 at the end, and then you add in the last digit. So n doesn't include the digits that I care about anymore, because I've already made a bunch of recursive calls. And the only thing I care about all the digits I've seen so far is that there's some smallest digit in them. And if I'm going to include this digit, it needs to be smaller than all the ones that I'm going to add on to the end later. So I think this value smallest needs to be the min of smallest and something. Now it's actually not the min of smallest and n%10. And why not? It's because we're supposed to be like skipping stuff along the way. And
okay,
now,
like it's smallest, like from on the right side, right?
Yeah, on the right side.
Okay.
And now I think we need to include the digit that we just saw. So then we need a third argument, which I think is going to be n%10. And then we did this times 10 plus n%10 thing. Okay, so let's see what happens with an example. Let's say I'm doing this one. And I do the yes case for the 7 at the end.
Okay.
For the 7 at the end, I'm going to add 7 to something else, a recursive call, where I still have never seen anything small, because I could pick any digit next. I could pick 9, I could pick 2, it doesn't matter. It's not going to care about the 7. It only cares about stuff after the 7, and there is nothing after the 7.
Yep.
So in the first recursive call, when I call, first I call near on 9, 8, 5, 3, 5, 7, and 10 and 10, right?
Exactly, yeah.
The next recursive call is going to be near on 985.357.035, where I still don't have an upper bound, but I did see the number 7, which is important because if I saw the 7 here, then I couldn't pick 9 later. Now, like one branch of this is that I go from here to near 9853, 10, 7, dot, 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 all the way to near 9, 10, 7. And I include the 9, and so I get 97. That's like one possible path. But there's another option where I do 9853 and keep the 5. If I keep the 5, then my whole sequence is going to end in 57, which means that everything to the left of the 5 needs to be smaller than 7. And I need to remember that 5 will be next. Okay, so let me tell you why I need this 5. As you look at this number that you're building from right to left, it's supposed to get smaller and smaller. The next thing that you include is allowed to be smaller than 7. But the thing you include after that has to be smaller than 5.
Oh,
well,
okay.
Yeah, you kept a 7 and you kept a 5. So this thing is going to end in 57. The next thing you include just has to be smaller than 7. But anything you include after that has to be smaller than 5. And you need to keep that 5 around in order to remember that it existed. You again have 2 options. You have the no or the yes case. I guess I'll draw the next yes case over here, which is that you could have 985, where 5 is now the constraint, and the next thing along is 3. So that would be any number that ends in 3, 5, 7. Or you could have another case, and the other case looks like, forget the 3, at which point the next digit I include just has to be smaller than 7, and anything after that has to be smaller than 5. In this version, you're not allowed to use the 5, because the 5 is now smaller than 5. So you can't build 5, 3, 5, 7. But in this version, you are allowed to include the 5, this 5, because it's smaller than 7. And so you are allowed to build 5, 5, 7. Okay, so we've built 2 numbers. 3, 5, 7 and 5, 5, 7 or whatever. You just take the bigger one. And if you can't choose between no 2 numbers, then you better just return the one that you have.